Hi, that we continue to study the correlation coefficient. So last time that we studied the Pearson's correlation. So Pearson's correlation basically that depends on the summation of the xi minus x bar times yi minus y bar. So today that we discuss the two other the correlation coefficients. One is Spearman's rho, and the other is Kendall's tau. So these two have the similar ideas. So the problem with the Pearson's correlation coefficient is typically in this situation on the left pane. So suppose we have 5 observations, and we have, the 1, 2, 3, 4, 1, 2, 3, 4, 5. But the fifth observation is really large. So actually, these observations that affects the Pearson's correlation a lot. Probably with this data, the Pearson's correlation R is around maybe 0.8 or even 0.9. But this is inappropriate because if we see just these 4 observations, it has negative relationship. But just this one very large observation makes the correlation coefficient very high. So the Spearman's rho, the idea is that to avoid this kind of too much influence from an outlier. Okay, so then what's the definition of Spearman's rho? The Spearman's rho is actually the Pearson's correlation coefficient, but for the order statistics. So we just think about the order. So you can see that these 1, 2, 3, 4, 5 observations. So this is the first smallest, this is second, this is third, this is fourth, and this is fifth. In terms of y value, it's the same. So this is the first, the smallest, and this is second smallest, third, fourth, and fifth. So just we don't use this numeric scale, but we only use the order. So I would say this is the order. So rank of xi, and this is rank of yi. So maybe just I write the Rx and Ry. Then Spearman's correlation is the correlation coefficient for these 5 observations. And you can see probably this correlation is very close to 0. So since the Spearman's rho is basically a special case of Pearson's correlation, the rho is still between -1 and +1, and all properties for Pearson's correlation hold. But if we think about the relationship between this R itself and the rho is probably very small, such as maybe 0.1 or I don't know. But the relationship between these two are not really simple. So it's somewhat related, but we use the rank or the order statistics for the rho. So we have slightly different definition. So we don't have the direct simple relationship between these two. Okay, so example. So suppose that we have 5 observations. So 1, 20, 3, 8, 6, 10, 8, 0, and 2, 12. Then, okay, so we just make a table for x and y. Then we take the rank. 1 is smallest, and the 2 is the second smallest. The 3 is the third smallest. The 6 is the fourth smallest, and the 8 is the fifth smallest. And the same for y. The 0 is the smallest, 8 is second smallest, the 10 is third smallest, and so on. Then to calculate the correlation coefficient, the usually good strategy is to take square. So rank is 1, 3, 4, 5, 2. So square is 1, 9, 16, the 25, and 4. And y, 5, 2, 3, 1, 4. So 25, 4, 9, 1, 16. And also the cross term. So rxi times ryi. So 1 times 5 is 5, and 3 times 2 is 6, and so on. So we can calculate the summation of the squares and summation of y squares and summation of xy squares. And actually this and this are always 55 because this is the summation of 1 square to 5 square. And also these are always 15 if we have 5 observations because this is the sum of 1 to 5. Yeah, then we can calculate the variance for Rx, and this is actually always the same, 2.5, because this is always 1, 2, 3, 4, 5 in some order. And the variance for Y almost also always 2.5 for 5 observations, but the Rx, Ry, the covariance term, so this is different, and this is the 36 and the minus 15, 15. So this is the same for every data set with sample size 5 and divided by 5, then 5 minus 1. So this becomes negative 2.25. So rho hat, so estimated rho is the negative 2.25 divided by square root of 2.5 times square root of 2.5. So this comes from here. So this is negative 0.9. So in this way, we can calculate Spearman's correlation in the same way as the Pearson's correlation. And the one good property is that the rho is invariant by monotone transformation. So if we think about the Pearson's correlation of X and Y, Pearson's correlation, the changes if we do the transformation of X and Y. The square root function doesn't change the order. You can see the square root of X is monotone increasing function if Y is equal to square root of X, then that is monotone function. And also the Y to the power 0.4 is monotone function again. But the correlation coefficient, Pearson's correlation changes from negative 0.856 to negative 0.826. But Spearman's correlation, since we only think about order doesn't change by monotone transformation. So this does not change, negative 0.9. So it's good. So if in mathematics, if some quantities are invariant, this is useful. Yeah. And actually, another formula for Spearman's rho is maybe easier to calculate rho. So we define the S. S is the difference between rank for xi and rank for yi. So typically, the sum of squared quantity S is small if X and Y are highly correlated. For example, if we have all observations in order like this, then S is equal to 0. If S is rather very large, maybe this case it's largest, so then S is very large. And rho is actually the 1 minus the S over the n cubed minus n. So n is sample size. Yep, so the testing on rho. So testing hypothesis H0 rho is equal to rho naught is done by simulating distribution of rho hat under H0. So this is not super easy if rho naught is not equal to 0, but if rho is equal to 0 is the null hypothesis. It's pretty easy to test because the rho is equal to 0 means just X and Y are not related. So linearly related. So just we randomly generate the Xi's and Yi's and simulate the distribution of rho. Then we can determine the rejection region, then we can test. But for the general case, rho is equal to rho naught. If you want to test this, we need some more complicated simulation, and this paper describes the method. In our language, we can still use the cor.test function to test Spearman's rho. So last time that we used the correlation cor.test for the Pearson's correlation, but just you can specify method is equal to Spearman, then we can test the Spearman's rho. So the S statistic appears here and p-value is here. So the p-value is 0.0833. So we cannot reject the null hypothesis that rho is equal to 0. So rank statistics doesn't have much information. So it's not numeric, so just order. So we don't have much information. So with 5 observations, it's probably difficult to reject unless we have very obvious relationship between X and Y. So even if rho is negative 0.9, we cannot reject the null hypothesis of rho is equal to 0. So only 5 observations, and the Spearman's rho doesn't have much information. So it's basically almost impossible to reject rho is equal to 0. So we need a larger sample size. So sample size was very small. So this is Spearman's rho.